Today we're going to look at something called equivalence relations, which is a way to help us generalize what we mean by equals. It's a very important concept in algebra. Let's get started. So before we can get much further into algebra, we have to understand this idea of equivalence relations. I'm going to assume that you have some basic knowledge in set theory, but if you need help with that, I have a video series going over set theory. Also, in this video, I'll have some additional exercises with solutions posted at the end, so look for those as well. So before we define what we mean by an equivalence relation, let's look at a context that may be a little bit more familiar to us, and that's congruence, like A is congruent to B mod n. So just to review what we mean by A congruent to B mod n, the definition says that n divides B minus A. Now what that also means is that B minus A equals n times something. Or sometimes we want to think about this as if I divide B by n, I get a remainder of A. So for example, let's let n be 5. And then one way you can think about this is let's take a gear that's got 5 teeth on it. And I'm going to take the integers and I'm going to wrap it around this gear. We'll start with 0 and we'll let 0 be this top gear. And so as I wrap the number line around this gear, or if you want to think about it as a clock with these hours, once I get past 4, I'm back to the 0 mark, and that's hour 5. And we can just keep going like this forever and ever, and we could go in the negative direction as well. So any of the numbers that line up on one of these teeth are congruent mod 5. So 5, for example, is congruent to 0, which is congruent to 10, which is congruent to 15, mod 5. And 6 is congruent to 1 mod 5. Now, you can think about it like the gears, or you could think about it like I was saying, when you divide 6 by 5, you have a remainder of 1. Or if I subtract 6 and 1 from each other, 5 divides that. Okay, so this congruence context is a great example of what we mean by an equivalence relation, because there's some things going on here that we may not exactly specify, but we can use this example to make a definition of equivalence relation and then generalize it to other contexts, as we'll see. So let's look at that. All right, so here's the definition of an equivalence relation. We're going to let squiggle, or tilde, what do you want to call it, be a relation that goes from set A to set A. And this is an equivalence relation if it follows these three properties. That if you take any little a in set A, little a is equivalent to little a, or a squiggles a. We call this a reflexive property. Now, if you think about what, if you think about the normal equals context, a equals a. If you think about congruence, a is congruent to a mod n. So those both satisfy a reflexive property. Secondly, we want that if a squiggles b, then we want b to squiggle a as well. We call this a symmetric property. Equals is definitely like this. 2 equals 2 because 2 equals 2, or x equals 2 because 2 equals x, and so on. This also works with congruence. A is congruent to b. Mod n means b is congruent to a mod n. The symmetric property is satisfied with both of those situations. And thirdly, if a squiggles b and then b squiggles c, we want then that a also squiggles c. We call this the transitive property. We know this very well from just normal equals. We use this all the time in just college algebra or standard algebra. This also works with modular arithmetic, with congruence. So if a is congruent to b and b is congruent to c, then we have that a is congruent to c. So these three properties are what we need to define a good definition of quote-unquote equals, congruence, equals, or other things that we will see. All right, so this time we're going to let S be R cross R. Now that means ordered pairs with x and y coordinates both coming from R. And we're going to say that the ordered pair x1, y1 squiggles the ordered pair x2, y2 if x1 squared plus y1 squared equals x2 squared plus y2 squared. Is this an equivalence relation? All right, so we're throwing in a new context. We have a new definition of equals here. We have to show these three things: reflexive, symmetric, and transitive. All right, so let's try. So first, let's look at the reflexive property. And all we need is that xy squiggles itself. And indeed it does, because x squared plus y squared equals x squared plus y squared. Let's look at symmetric. So we say if x1, y1 squiggles x2, y2, then we need the opposite direction to work. We need that x2, y2 squiggles x1, y1. We get to appeal to just good old-fashioned equals, right? And so if x1 squared y plus y1 squared equals x2 squared plus y2 squared, then of course we can flip that around to get the other direction. So I get x2 squared plus y2 squared is the same as x1 squared plus y1 squared. Okay, so all I did was just rewrite it and flip it. And I can do that because this is just, I'm using the normal sense of equals that we know is symmetric. We've been doing that for years now. All right, the third thing, transitive. And in this particular example, the transitive property is going to be about as simple as the last two. So this time we need 3 points. And so what I'm going to just say is suppose that x1, y1 squiggles x2, y2, and x2, y2 squiggles x3, y3. Can we show then that x1, y1 squiggles x3, y3? Yeah, we definitely can, because again, we're just doing this standard version of equals. We can just say then, I know that x1 squared plus y1 squared equals x2 squared plus y2 squared, and that equals x3 squared plus y3 squared. So, by the definition that we set up, that means that x1, y1 squiggles x3, y3. There. This is an equivalence relation. So this is a new way to define equals. And so we could come up with an example. Let's see what kind of things are equivalent to 1, 0. Well, let's see. 1 squared plus 0 squared is 1. So anything that, if I say the first coordinate squared plus the second coordinate squared and I get 1, then it is equivalent to this point. So we'll say this is equivalent to 0, 1, for example, or negative 1, 0, or root 2 over 2, root 2 over 2 will work. And there's a lot of other things that 1, 0 is equivalent to in this context. All right, so let's look at another example. This time we're going to let S be the set of all people. And we pick X and Y out of S, so the X and Y are people. We say that X squiggles Y if X and Y were born in the same town. Is this an equivalence relation? Okay, I think this is pretty simple to show. If we want to show reflexive, we just need that, is person X born in the same town that person X is in? Yeah, okay, so this is super easy to show, okay, because person X was born in the same town as person X. Okay, now how about symmetric? So this time we need to show that if person X squiggles person Y, then person Y squiggles person X. Okay, I think that's pretty easy to show because we can say if X is born in the same town as person Y, then Y is born in the same town as X. So we just showed that if X squiggles Y, then Y squiggles X. All right, now the third thing we need to show is just the transitive property. All right, so we need to suppose here that X squiggles Y and Y squiggles Z, a third person. Okay, so in other words, we're going to say, let's let X born in the town of person Y and Y born in the town of person Z. Okay, well, the only way this is possible is if person X was born in the same town as person Z, right? Because the town is the same. And so that's it. This is another equivalence relation. We have shown reflexive, symmetric, and transitive properties. Now the only question then is, in my mind, is, well then, who is equivalent here? So if I take all the people equivalent to person X, what does that mean? Wouldn't that be like just all the people born in whatever town person X was born in? So this time we're going to let S be the set of lines, and we're going to take two lines, L1 and L2, and say that they squiggle if they are parallel. Is this an equivalence relation? All right, so again, we got to show the three things. Now, remember, if I take a line, let's say L1, I can write it as y equals mx plus b. We get this an equation. Two parallel lines means that their slope is the same. Okay, so here we can say L1 squiggles L2 if their slopes m1 equals m2. Their slopes are the same. Okay, so now I think that makes it a little bit easier to show that these are indeed an equivalence relation, because if I take L1, it squiggles L1 because its slope equals its own slope, right? Okay, symmetric, when we say if L1 is parallel to L2, then L2 must be parallel to L1 because, so I'm giving a mathematical explanation for this, even though intuitively we can probably visualize why this would work. But because if M1 equals M2, that's what we get when we say L1 squiggles L2, then M2 squiggles M1. Okay, so symmetric. And then thirdly, transitive is just as simple. So if L1 squiggles L2 and L2 squiggles L3, then we know L1 squiggles L3, because if M1 equals M2 and M2 equals M3, then we know that M1 equals M3. So now this is an equivalence relation as well. And we can say what kind of lines are equal to each other? The ones that are parallel. I'm going to give you a few additional exercises of equivalence relations, and at the end of this video you can find the solutions to those. Okay, now I want to introduce another definition. So we're going to let squiggle be an equivalence relation on S this time. And then for A in S, the equivalence class of A, and this is a little element A, is the set we can write it brackets A, and this is B in S where A squiggles B. Now what does that mean? That means the equivalence class of A are all the things in S that squiggles A, or A squiggles that. In other words, these are the things that are equivalent to A in this set. Now that sounds weird to us with our normal definition of equals, because the only thing equal to 0 is 0. The only thing equal to 2 is 2. But when we have other contexts, we have seen, like parallel lines, there can be a lot of lines equivalent in this idea. For example, here, let's consider the integers with A congruent to B if 4 divides B minus A. Now we've already seen this. This is just what we mean by A is congruent to B mod 4 in this case. So what we want to do here is determine the equivalence classes with this congruence relation congruence mod 4. Now remember earlier I said one way you can think of modular situations like this is like a clock with only 4 hours on it, starting with 0. Remember, these are also, when you divide by 4, what possible remainders can you have? So the remainders I could have are 0, 1, 2, 3. Past that, we just keep reducing it. So for example, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and we can keep going on and on and on. And two things that are in the same hour are congruent mod 4. Here we might say equivalent. So if I write this symbol, the things congruent to 0, this is the set of all things that are congruent to 0 with this equivalence relation. I could say, well, 0's in there for sure. 4, 8, 12, and so on and so on. And I could play this game with my other values as well. And I have characterized the equivalence classes of congruence mod 4. And basically, one way to think about this, the way I like to think about this, is think about that from this situation, we take a box that we label 0, and all the stuff that is congruent to 0 in this context will go in this box. So for example, I put 0 in there, and 4's in the box, and 8's in the box, and 12's in the box, and 16's in the box, and so on and so on. But this time, instead of playing with the things in the box like we normally do, 0, 4, 12, 8, I want to play with the box itself. So this box labeled 0 is the object that I'm interested in. So I have some other boxes here. I have a box labeled 1. I have a box labeled 2. And a box labeled 3. And I don't need a box labeled 4 because the box labeled 4 is actually the same as the box labeled 0. They would be the same thing. So 0 is enough to represent the equivalence class of 4, the equivalence class of 8, and so on. And again, what you're wanting to do is take your integers, and you take each integer one at a time, and you're putting it in a different box. When you do that, and we put it in a box based on its equivalence class, in other words, what it's congruent to mod 4. When I do that, I fill up each of these boxes evenly. Every integer falls into one box, and no integer falls into more than one box. For this reason, we say the equivalence classes partition my set, in this case the integers. These equivalence classes partition the integers, meaning that nothing falls in more than one category, and everything does fall in a category. And now I can treat my equivalence classes as the object, not the things in the box. Does that make sense? I hope it makes sense. So let's revisit some of the equivalence relations we looked at earlier and see if we can determine their equivalence classes. So here we talked about the ordered pairs congruent if x1 squared plus y1 squared equals x2 squared plus y2 squared. Now, it's okay if you didn't recognize that formula, x1 squared plus y2 squared, but I remember this from algebra for geometry, that x squared plus y squared equals r squared is the equation of a circle with radius r. So earlier when I asked, I said what's equivalent to 1, 0? Well, if you think about 1, 0, 1 squared plus 0 squared equals 1 squared. That would be like something that falls on a circle of radius 1. On a circle of radius 1, I have the point 1, 0, and 0, 1, and negative 1, 0. And here is root 2 over 2, comma root 2 over 2, and a bunch of others. And in fact, the equivalence class of 0, 1 are all the points that lie on the circle of radius 1. And so I could have equivalence classes based upon my radius. I could have an equivalence class of 1/4, for example. I could have an equivalence class of 2. And the things that are in this equivalence class are just the points that lie on the circle of that given radius. What about the parallel lines? Couldn't we say the equivalence class of a parallel line are all the lines that have that exact same slope? In other words, all the lines parallel to this particular line. And so I'd represent my equivalence classes just based on the slopes, because a given slope gives me a whole bunch of lines parallel to that one slope. All right, I have some additional exercises of equivalence classes. The solutions to those are at the end of this video as well. I hope this makes sense. Hope you're doing okay. Let me know if you have questions. Feel free to leave a comment. Feel free to like. Feel free to send me an email. I'd be happy to help. This is a great concept to understand. You can do it if you just keep working hard. Thanks for watching. We'll see you next time.